Okay, perfect. All right, so these sessions are going to be 1 hour long, and most of them are going to be one chapter. Some might be two chapters, some might be three chapters. I'll fly through some chapters just because you don't really need to know it. I'll pick and choose certain things from certain chapters that can help you on the SPI. Other chapters, I'm literally going to go page by page from the Edelman Green Book. Today, we are going to kind of run, but not really, through these two chapters, chapter 3 and 4 in the Green Edelman book. And it's just to get the basis, like the foundation of certain things, because I know the beginning of the book is a lot of terminology, a lot of formulas. It's a lot of stuff just being tossed at you at once, and it can get really confusing. So I'm going to try to clear that up first before we get into the big concepts which are on the SPI. So I'd like to normally start off by explaining my opinion of the SPI. I know that we all pretty much hate it. You know, it's physics, it's math. Well, not really math, but we think it's math. Everything is relationships. They tell you don't memorize, that you have to understand the information. But then when you go out and try to look for someone to explain the information so that you understand it, there's really nothing there. Like no one really breaks it down, you know? So it's kind of like, well, what's going on? You want me to understand it, yet there's really no one that's really teaching it that way. All of those things are true. You do have to understand it. Memorizing doesn't really work for the SPI. There is no math, so don't worry about that. It's more about just relationships, and then some relationships with numbers, but it's really just honestly just relationships. So for the SPI, personally, I feel like they're just trying to test that you know what you're doing when you're making adjustments. You know, anybody can start turning knobs. You give anyone an ultrasound machine and they'll just start turning knobs because they're just there, you know. But are you doing the right movements, the right adjustments? Um, are you making things worse? Are you making things better? You know, because you can easily make things look worse. Easily. All right. Like it's the simplest thing to make something look bad. You want to make something look like it's aliasing, you can do that by just the turn of one little knob. Even though it could be really slow velocity, you can make it look like it's aliasing. And now you're kind of wondering, wait, this is aliasing? Am I looking at something stenotic? You know, so for the SPI, what they really want to know is, hey, are you making the right adjustments? Do you know what happens when you turn up your scale? Do you know what happens when you turn down your gain? Do you know what happens when you start messing with your PRF? And if you know those things, do you know when you're supposed to do those things? You know, at the right moment, the right time. Because we have presets, and presets are settings for the average study, but they don't take into account non-average studies. When you have a really heavy patient, when you have someone with a lot of pathology, presets don't really work for that. So you have to go ahead and make the changes and customize the preset for that specific study. Okay, so the SPI is about that. It's just asking you, when you start playing with the machine, do you know what you're doing? That's really just it, you know. So I think it's fair game. You know, we don't want to take it, and trust me, I didn't want to take the SPI, but in some ways, it's fair game for us to know what we're doing. It's one thing to scan; it's another thing to mess with the machine. Okay. Um, so one of the first things is when we start messing with frequency. All right. So we all know that high frequency is supposed to be shallow, and I'm writing on the board, so you all should be seeing me right on the board. High frequency is supposed to be shallow, and low frequency is supposed to be deep. Okay. So when you have a really heavy patient and you're scanning with this, you right there, you're showing that you don't know instrumentation, you don't know physics. Okay, right there, it kind of proves that. All right, so that's why it's important to know some relationships. And later on, when I get into chapter 6, which is attenuation, I'll come back to this in the conversation of high frequency and low frequency, because it really is a great conversation to have, the concept of attenuation. All right. One of the most important things is reading formulas. And some of you may know how to read them, some of you may not. My experience is that most don't know how to read formulas. I'll try to make it bigger. This is as big as I can make it without kind of going overboard. So let me know if that works for you.
That's great. Thank you.
Reading formulas. So you'll notice that throughout the book, there's a ton of formulas, okay? And formulas are honestly a shortcut. They're not a bad thing. They're actually a good thing. I would prefer a formula over a page of context and information. Okay, so now the question is, do you know how to read them? Okay, because formulas are actually going to give you relationships. So let me just write this other formula here, which is weight equals food over exercise. Okay, so I really like to eat. I mean, all of us really like to eat. And it's always funny when someone tries to say, we have things in common, we both like to eat, or it's kind of like, well, who doesn't like to eat, right? But anyways, so weight equals food over exercise. And this is a formula you probably have never seen before. And I'm sure this formula exists, okay? But for me, I made it up, all right? But if you know how to read this formula, you can extract the relationship from it. So when you read a formula, draw an imaginary line where that fraction is. Just draw an imaginary line there. And that imaginary line divides the formula into a top and a bottom. You have a top portion of the formula and a bottom portion of the formula. And then you have these equal signs that separates, the left from the right, basically. So you draw that imaginary line, top and bottom. If you're on top, you are directly related. And what does directly related mean? It means you will behave the same way. If one goes up, the other one goes up. If one goes down, the other one goes down. So directly related means it will behave the same way. If you're on the bottom, you are inversely related, which is the opposite of directly. And bottom is the opposite of top. So if we're on the opposite side, then things should be the opposite. Okay. And that's a very common theme with a lot of things in ultrasound physics. If you know one part of something, you can then just apply the opposite rule and just say, well, if the other thing is the opposite, then everything else must be the opposite. And I'll point that out as I go through different concepts for the next 3 to 4 weeks. All right, so if you're on top, you're directly related. If you're on the bottom, you're inversely related. And what does inversely related mean? It means you will behave the opposite way. So if one goes up, the other one would do the opposite. It'll go down. Or if one goes down, the other one would do the opposite. It'll go up. So let's just look at this. If I eat more food, I gain more weight. Okay, directly related. If I eat less food, I would lose weight. Okay, directly related. They both behave the same way. And for inversely related, now here's the trick. I'm not referring to these two things being inversely related. Okay, these two things are not inversely related. What's inversely related is always the result. So whatever is on this equal sign, that's what gets affected. Okay, not this guy right here, because I can exercise more, but that doesn't mean I will eat less food. I can choose to eat more food. They're independent of each other, I can do whatever I want. They're two separate things. So what gets affected is the result. If I exercise more, I lose weight. Or if I exercise less, I gain more weight. Okay, so that is the relationship. That is how you read a formula. Now let's relate this to ultrasound. Wavelength equals propagation speed divided by frequency. I'm going to draw an imaginary line. I have my top from my bottom. My top is directly related. My bottom is inversely related. So what does this mean? It means that if my propagation speed goes up, so does my wavelength. Or if my propagation speed goes down, so does my wavelength. Or if my wavelength goes down, so does my propagation speed. It can go either way, okay? They're both on top, they're going to be directly related. Now, the bottom one is inversely related. So if my frequency goes up, my wavelength would have to go down, meaning it gets smaller, it gets slimmer. Or if my frequency goes down, my wavelength would have to go up. Okay, so formulas are there to give you the relationship. That's it. There's really no math involved. It's always just relationships. And you'll see that a lot when you do practice questions. They'll say your frequency went up, or your frequency went down, or your depth went deeper or shallow. It's very like general terms. Sometimes they'll give you numbers, but it's mostly this general concept of higher frequency, lower frequency. They don't say, 15 megahertz versus 3 megahertz. Sometimes they'll throw that in there, but it's more about just that general concept of something being bigger and something being smaller. So when you know relationships, you can easily when you know the formulas and how to read them, you can easily knock those things out. And I can prove that this formula here is true. So frequency is tied to a 1 second interval. Okay. I cannot draw 1 second. Second is a time unit, so I can't just draw 1 second. But let's pretend that each of these lines is 1 second. So let's just pretend this is what 1 second looks like. And in A, I'll do this. Okay. So if I wanted to know my frequency here, I will count my number of cycles. So I have 2 cycles. And let's say that in B, I do this. And my frequency here is 1, 2, 3, 4, 5. So my frequency in B is 5. So if I were to say which one is a low or high frequency, A would be my low frequency and B would be my high frequency. I have more cycles in B. So look what happened here in terms of the wavelength. The wavelength is the measure of the beginning of the cycle to right when the cycle will repeat itself, which is right here. That is my wavelength. And in B, the same thing, the beginning of the cycle till the cycle repeats itself. Look how my wavelength is bigger here than it is down here. And there shows that inverse relationship where the frequency is lower in A, but the wavelength is bigger. And in B, the frequency is higher, but the wavelength is smaller. And the way I like to teach this is you're limited to 1 second. So if you want to fit more cycles into that 1 second, you have to squeeze them in there. You don't stretch them out. If you stretch them out, they take up more space. So if you want to fit more cycles in there, you squeeze them in there. And when you do that, what happens when you squeeze something in? It gets slimmer, it gets tighter. And that's why my wavelength becomes smaller, because I'm making it tighter, I'm squeezing more in there. Okay, so the formula tells you that just by reading it. Instead of drawing all of this out and trying to explain it, I could just say, hey, know the formula and know how to read it. And that's it. So please be grateful for formulas because they really just give you the relationships flat out. You don't have to think about it. You don't have to guess it. As long as you know certain formulas, you can just forget about memorizing the relationships. Just write out the formula and read the relationship from it. Does that make sense to everyone, or is there something somewhere where I lost you? Talk to me.
It's good. Makes sense.
Okay.
It makes sense. It's just that when you was pointing out, you went from wavelength to frequency. I see how. I mean, I see what you was pointing out how long the wavelength would be, but I was
Mhm.
concerned about the frequency. You didn't point out the frequency. You just said it went up or down, but how do you know?
Okay, let me see if I still have it here. Well, look at my frequency is my number of cycles. I have 2 cycles here, so I wrote my frequency as 2.
Oh, okay,
And in B, I have 5 cycles here, so I wrote my frequency as 5. And
okay,
if I compare 2 and 5, well, this one is higher and this one is lower. So that's how I
okay,
made one higher and lower.
okay, gotcha.
Okay. Now there's another formula that I want to cover, and it's the PRP formula. Actually, let me do the SPL one because it's more common to have the SPL formula. So in the SPL formula, you'll notice that there's no top and bottom. There's no fraction there. Okay. But the rule still applies. You draw an imaginary line and you have a top and you have a bottom. But in this case, there's no bottom, so you exit out. Okay. No problem. So everything is just on top. So things are directly related. Okay. Everything's on top is directly related. Now, excuse me, here's the trick. Here's where you have to pay close attention. Okay. Because things that are directly related, you must remember it's with the result. This is a formula that is going to give you a result. So all of these relationships about being directly related is only with the results. When we had the wavelength formula, it was easy to see that because we only had one variable, right? One on top and then one on bottom. So it was easy to say, oh yeah, they're affecting the wavelength. In this one, we have 2 variables, okay? Number of cycles and wavelength are not directly related, okay? Remember, they're only directly related with the result. So how is number of cycles and wavelength related? They're not, okay? They're not directly related. They're not inversely related. They're just independent. They're doing their own thing, okay? They are part of the formula, but because they're on the same side, on the right side, there is no equal sign between them. So they don't affect each other. What they affect is this guy. Okay. So try to think of this, try to look at this formula from this perspective. SPL equals number of cycles. Try to look at it like that. Boom, directly related. Or SPL equals wavelength. Boom, directly related. So try to maybe see it that way, to remember that they're only affecting this guy. So then what happens here? Well, if my number of cycles goes up, my SPL goes up. If my number of cycle goes down, my SPL goes down. Okay, nothing happens here. If my wavelength now decides to go up, then my SPL goes up. Directly related, remember? They affect the result. Or if my wavelength goes down, my SPL can go down. Okay, directly related. But just because the wavelength goes up does not mean number of cycle goes up. Does not mean number of cycle goes down. Number of cycles can do whatever it wants to do. It can go up, it can go down, it can go side to side, it can do a skip and a hop and a hippity pop. It can do whatever it wants to do. All right. So so not directly related, okay? They're independent of each other. So whenever you look at formulas and you see like a whole bunch of things on one side, don't say, oh, all of those individual things are related to each other. No, they're only related to my result. Okay, so I just need to be very clear about that. All right, enough about formulas because now you should be able to read formulas. Okay, now anytime you look at a formula, look at what's on top, look at what's on the bottom. Okay, and then that will give you the relationships, and that is what you based your knowledge on relationships, because every question is going to be about that. All right, let's knock out some terminologies, because there are quite a bit in these chapters. There's a period, there is a wavelength, there are cycles. Actually, let me do frequency first. Frequency, and there are cycles. This is the gist of chapter 3, this part right here, and then I'll give you chapter 4. So period is a period in time. That's how I remember it. My unit is time. A period in time, like once upon a time, you know? So a period in time. A wavelength, this one is actually even easier than a period, because a wavelength literally tells you what it does. It's the length of a wave. And the length can only be measured as a distance. Any length is a distance. Then frequency, you know, pretty much is from the word frequently, right? When you say I do this frequently, then it's like, oh, okay, well, how frequently do you do it? And you say, oh, I do it once a week, twice a week, you know, whatever, whatever. So you're giving them how often you do something. So frequency is pretty much that, is how often, but in this case, how many of something. And because we're talking about sound, we want to know how many cycles. Okay, and frequency is always tied and limited to 1 second. So we basically get how many cycles, the number of cycles in 1 second. So frequency will always be how many cycles in 1 second. That is frequency. Okay, always limited to 1 second. Because there's a little tricky question. I don't think it's in the SPI. I think it's in the review apps and websites, where they'll give you something like this, and they will say that this is 2 seconds, like this line is 2 seconds. And they'll ask you, what is your frequency? And most of us will say 4. My frequency is 4. But it's a tricky one, because frequency is how many in 1 second, and they're giving you 2 seconds. So then you just go by logic and you say, well, if 2 seconds has 4, then 1 second must have 2. You know, half the time, half the number of cycles. So my frequency is actually 2. Again, I don't think that's in the SPI, but I know I've seen that around in some review questions. So just remember it's per second. And then number of cycles are the individual waves. Okay, so whenever we look at this, we count the individual waves. Those are cycles. Here's the cool thing about these terms. Let's start off with period and wavelength. Period is a time and wavelength is a distance. Time and distance have like the most specialist of bonds, because everything we do is a time and a distance. Like, let's say I want to travel somewhere and it's 1,183.8 miles away. Just a random number that means nothing, okay? 1,183.8 miles away. That's a very far distance. And to go a very far distance, I'm probably going to need a lot of time. Whereas if I just want to go 1 block away, I can get there pretty quickly. Why do we, decide to go to one particular restaurant versus another? Or why do we order food from one place versus another place? And let's just say that both places are like absolutely great. Why do we pick one over the other? Chances are we're picking it because of the distance. It's from our house. Okay, if it's really far away, we know it's going to take more time. And maybe we're hangry, right? We're in that stage where we're hangry and we don't want to wait. And we say, no, I gotta drive 30 minutes. No, I'm not gonna make it. But if something is around the corner, then perhaps it's fine. Like, oh, you get there really quickly, get your food. So time and distance have that special bond where everything is time and distance. Okay. Open up your maps, put a location. What are the two things it tells you? Time, distance. That's it. Everything is time and distance. So because of that, these two guys will always walk in each other's shadows. Okay. So if I draw this here and I want to measure my wavelength is from here to here. That is the distance of one cycle. That is my wavelength there. Okay, the length of my wave. That's it. And all you need to know is just one. You don't need to know all of them because they're all identical. They all follow the same suit as the first one. That is my wavelength. And in that same place, that little line right here, in that same place, I measure my period. Same place. Okay, it's just a different unit. But in the same exact place where I measure my wavelength, I measure my period. So if my wavelength decides to do this, it becomes really big. So my wavelength got bigger, right? Look how much it stretched out. But if my wavelength got bigger, that means that my distance became longer. And if my distance is longer, I need more time to travel that distance. All right, so it's a very, very common sense and logical concept that if there's more distance, there needs to be more time. Okay, so they walk in each other's shadows, so they are directly related and they're measured in the exact same place. Only difference is they use a different unit of measurement. One is time, the other one is distance. But that's it. That's period and wavelength. Okay, no need to confuse it anymore. Just know that they're in the exact same place. And then with frequency, we just count, as I did earlier, we count the individual cycles. All right. There's this whole thing about what's determined by the source, what's determined by the medium. You don't really need to know that, but if you want to know it, just remember the exceptions to the rules. Okay, this guy is the exception to the rule. This guy is determined by the medium plus the source, and then propagation speed is determined by the medium. Everything else is the source. So just remember that these two are the exceptions, medium and source, and propagation speed just the medium. Just remember these two and know that everything else is just source. That way you don't have to remember, oh, frequency is source, period is source, blah, blah, blah is source. No, no, no. Wavelength, medium and source, propagation speed, medium. Everything else, source. All right, so we just start cutting down on the things that we need to remember. All right, so here's where things start to connect with chapter 4. All of these guys wanted to grow up. All right, they wanted to grow up to be better things, better terms, I guess. Right, they wanted to be smarter and bigger and stronger. So period turned into post duration. Wavelength turned into spatial pulse length. Frequency turned into pulse repetition frequency. And cycles, doesn't get left behind, turn into pulses. So this is where we take the next step. This is when we go from cycles to pulses. And what are pulses? Pulses are bundles of cycles. So we are no longer looking at the individual waves. Now we're looking at the bundle itself. So when we start measuring things in pulses, we don't measure each individual one. We just measure that bundle together. Of course, if you change the individuals then end up changing the bundle. Okay, but at the end of the day, we measure the bundle, and you'll see what I mean. So period becomes pulse duration, the duration of my pulse. And whenever you look at the duration of something, we measure it in time. same as period. It's just a bigger brother. Okay, so everything just stays the same. We're just looking at pulses now. And because we're looking at pulses, we use different ways of measuring it, different terms and things like that. But we still want to know the basics. We still want to know the time, the distance, how many. That is the foundation of pulses. So pulse duration is just period, but for pulses. So we call it a pulse duration measured in time. The wavelength now becomes the length of the pulse. Before it was the length of the wave, now it's the length of the pulse. And what is the unit for length? Distance. Same as wavelength. That's why it's just a bigger brother. Frequency were how many cycles in 1 second. Now we still are limited to 1 second because frequency is still in there. But instead of number of cycles, now we want to know number of pulses. Okay, so again, we're just changing a few things around. Number of pulses in 1 second. Okay, is how many times does the pulse repeat itself? That's basically it. And then a pulse, again, a bundle of cycles. What's really cool about these terms down here is that they're telling you their focus on the pulse. All of them have pulse in there because that's what they're measuring. They're measuring a pulse. Okay, so it's very hard to forget that we're talking about pulses because they literally are telling you, hey, this is what I'm interested in. So we went from individual cycles now to the bundle of cycles. So what does that look like? Well, now we get a bundle and now there's a break. Then we get another bundle and now there's a break. Now the individual waves inside this bundle can change. You can have 4, 5, 2, and you can also change the wavelength. So instead of being this wide, they can be this slim, right? Still 3 cycles, but maybe they're really narrow, small wavelength, like that. So I can keep the same number of cycles in each pulse, so 3 and 3, but I can change the wavelength in them. Okay, so you can mess with this, but nonetheless, whenever I want to ask about my pulse duration, this is what I'm asking for. The beginning of the pulse to the end of it. The beginning of the pulse to the end of it. So I'm focused on the entire bundle. I'm not focused on, oh, this is my pulse duration. It's like, no, that is not your pulse duration. Your pulse duration is the entire bundle. And just like period and wavelength, look at pulse duration and spatial pulse length, time and distance. So in the same place where you measure your SPL, this right here is the same place where you measure your pulse duration. It's the equivalent of period and wavelength. So they're going to behave the exact same way. If my SPL gets bigger, it means that there's more distance. That pulse took more distance. And because it's more distance, it needs more time. Oh, thank you. Woohoo! I just saw the message. I appreciate it. I try my best. So in the same place where you measure the SPL, it's the same place where you measure your pulse duration. Okay. So with that, you can say directly related. So anytime they ask you about SPL, they can ask you about pulse duration. Because if I change one, I change the other. It's not like I somehow change my SPL and don't change my pulse duration. It doesn't work that way. When something is directly related or inversely related, the moment you change one, the other one automatically changes. It's a domino effect. Okay. Any relationship is a relationship. Only if they're independent, then it doesn't matter. But if I change one thing and I know it's tied to something else, that something else also changes with it. Okay. And this is how we get to the 3 bigness. Oh, and by the way, this also has some, what determines the source, the medium and things like that. All of them are the source, except this one. okay? SPL is not determined by the source. SPL is determined by the source plus the medium. But everything else is the source. So if you have to remember that, again, remember the exception. SPL is determined by the source plus the medium. And I can prove it because SPL has the formula of number of cycles times the wavelength. And the wavelength is determined by the medium and the source. So if this is determined by the medium and the source, this will also have to be determined by the medium and the source. And how can I prove wavelength is determined by the medium of the source? Because of the formula. Propagation speed divided by frequency. Frequency is determined by the source. Propagation speed is that other exception that's determined by the medium. So inside the wavelength formula, you have a medium and you have a source. And that's why wavelength is a medium and the source. And because SPL has a wavelength, then that carries over. It's like we're just inheriting things, you know? That's basically what it is. If you want to know who you are, know who your your background and stuff like that is, you know? So that's basically it. We're just doing this ancestral search here. And that's how things just trickle down. The three bigness, okay? Let's discuss the three bigness here. So the three bigness are power. Oops. Let me write it like this instead. Intensity equals power equals amplitude. And I'll leave the other part for later. Okay. Now, a lot of times I like to write a lot of things in formulas because it just tells me what the relationship is. So I'll make up some formulas, okay? And I'll tell you when they're made up. This one, it's kind of made up. Like it's supposed to be proportional. The book writes it like this, proportional. I just write it as equals, okay? Because that's pretty much what it means. So this is kind of a made up formula, but then kind of isn't. So I write it out, intensity equals power equals amplitude. There are two things to know about this. One are the relationships, knowing how to read it. And if you see that they're all equal to each other, that should tell you that the moment you change one, you change everything. Okay, the moment I change intensity, this changes and this changes. The moment I change this one, this changes and this changes. And the moment I change this one, this changes and this changes. Okay, they're all equal to each other. So it's an automatic. In no way can you say I'm going to change my power, but not my intensity. That's not going to happen. And on our ultrasound machines, we can change this. We can change the power. We don't change the intensity, but we change the power. And the moment we change the power, we change the intensity, even though we're not hitting a button that says intensity. Okay. So that's the first thing to know. Know that they're all going to be proportionate to each other. They're all going to behave the same way. The second thing to know is that amplitude is squared. Okay, and it's very important to know that because if my intensity doubles, my power doubles. They're proportional, right? They're the same thing. My amplitude will double because it's all proportionate, all the same thing, except that it will double squared. So in actuality, my amplitude quadruples. And that's a big difference, right? Like in a question, that can be a very big difference. So you have to remember that they're all directly related and that amplitude is going to be squared. Okay, and then you can do it by getting smaller. So instead of doubling, I'll get cut in half. Then my power gets cut in half. Then my amplitude gets cut in half squared, which basically means half times half equals 1/4. So even though everything else got cut in half, this one came down to a quarter of what it was. And it kind of makes sense, right? Like if everything doubled, this one quadrupled, which was a lot more. And everything got cut in half, this one got cut into a quarter, which is a lot less. So it keeps its consistency, its predictability. Okay, so again, just remember this little sequence here because it shows you the relationships. And just remember that amplitude is going to be squared. And with that, that will get you through any intensity, power, amplitude question because all they're really going to ask you are relationships for that. Now, they could ask you about the intensity formula, okay? Now, what I wrote here is a relationship formula, but intensity actually has a formula, like it's an actual formula, this times this, blah, blah, blah. And that formula, the reason why I write it like this is because that formula, half of it is already here. That is my intensity formula, power over area. So you already know half of it by knowing that power is there. All you would have to remember is that area goes at the bottom. So area is inversely related to intensity. Okay. And that's how we get that magnifying glass science experiment, which is when you have a magnifying glass and you put it over the sun, it starts a fire. And the reason for that being is because you have sun energy, like sun rays, right? Sunlight energy just coming down. And it's all spread out in an area. But when you have a magnifying glass, you take that area and you make it small. So you take all that energy that was once spread out and you've combined it into a single point. So basically my area went down, right? Because it started out big and the magnifying glass made it small to a single point. So my area became smaller, so it went down, and that caused my intensity to go up. So I just increased the intensity by doing that. And I increased it so much that it became really, really strong enough to burn. Because on its own, all of this sunlight doesn't do anything. You don't see forests burning into flames every time the sun comes out, right? It never happens. It's always when somebody either leaves fire or glass or something behind that then takes the energy and focuses it, but otherwise that sun energy is fine on its own. It's only when I decrease that area, I take all that energy and combine it into a single area. And then the formula proves that to me because the formula literally tells me that intensity is inversely related to area. All right. Any questions? We're very quiet, and that's okay. But I like some back and forth. So any questions, anything to keep me going? Any standing ovations maybe?
This is great. I
Good,
like the
good.
magnifying glass. The
Oh, okay, good.
small area, or big intensity. You're doing great. Keep going.
Thank you. Awesome. So anybody, am I losing anybody so far with something?
No.
We're almost done with the first class, so just bear with me a little bit. We're almost there. So some classes are going to be an hour long. Some might be a little bit longer than an hour. Some might be, a little shorter than an hour. So it just depends on how much we're covering and if we have questions and things like that. But it all averages out, so we'll be good. The next thing to remember that they always tend to ask is the relationships and propagation speed. So propagation speed is determined by the source. Okay, that's one thing. But now they want to know what relationships does propagation speed have with certain terminology, certain other concepts and stuff like that. And there's really just remember this. Propagation speed. I always write equals. It's like a habit now. Stiffness and stiffness is pretty much the same. It's the same thing as bulk modulus. All right. And look, I write them equals and they're on top, so they're directly related. Okay. So stiffness is directly related to propagation speed. And bulk modulus because they're the same thing. Now there are three other terms that they can toss around: density, compressibility, and elasticity. Now they can ask you about these three terms: density, compressibility, and elasticity. These three things are not stiffness and bulk modulus. So your job is to remember that these two guys are the only ones that are directly related. That's your job. So anytime they bring up something else, okay, it's going to be inversely related. Because these are the only guys that are directly related. So your job is just that. Remember the one that is directly related. Because if they ask you about anything else, it's just the opposite. Okay, so you don't have to remember that density is inversely related, that compressibility is inversely related, that elasticity is inversely related. You don't have to go through that mental workout. You can just say, if it's stiffness and bulk modulus, it's directly related. If it's anything else, it's inversely related. Okay, that's it. That's all you have to remember. That will be an easy question in the SPI that they'll just throw in there, you know, little fillers that they'll use. Now, the whole depth and PRP and PRF thing, I get a lot of students who like, you know, lose it when it comes to that. And yeah, some of this stuff is confusing, man. I'm not gonna lie. So here is a straight up made up formula. Like I'm not even gonna, you know, dress it up for you. This is a made up formula. Depth equals PRP divided by PRF. Now, PRP has its own formula. PRF has its own formula. This right here, this made up formula, is for relationships. All right. I made it up and it's solely for relationships. Because you're not really going to be asked a PRF formula because the numbers are high. It's like 77,000 divided by, what is it? 77,000 divided by imaging depth is the PRF formula. You know, so you're not going to sit there and start dividing things by 77,000, right? It's not going to happen in the SPI. All right, unless you're dividing by tens, because then you just eliminate zeros. But it's not going to happen. And then PRP is number of cycles times period. Again, you're not really going to be asked to do the math there. Just be aware that they have their own formulas. What you're looking at right now is a made-up formula for the relationships, because that's what really matters, to be honest, the relationships between these guys. So if you look at this, you'll see that I can divide this into a top and a bottom. And again, things on top are directly related, things on the bottom are inversely related. And I put PRF in the middle, okay, because I kind of want to illustrate that it is inversely related to both. So I kind of put it in the middle. I didn't pick a side. So things on top are directly related. That means that if my PRP goes up, my depth goes up, okay? And PRF is inversely related to both. That means that if my PRP goes up, my depth goes up, my PRF goes down. Okay, inversely related. So I can just say like this: this goes up, this goes down. Or this goes down, this goes up. Or this goes down, this goes up, this goes up. Okay, just inversely related.
No question.
Yeah.
I know you made this formula up, but does that, it still runs true though because of the formulas of the individual PRP and PRF, is that correct, with depth?
So the PRF formula does prove true to this, because that PRF has depth in it, but PRP, it's just number of cycles times period. It has nothing to do with, at least in the formula itself, it doesn't bring depth and PRF in there.
Okay.
The thing is, the reason why I made up this formula is because the way that you change your PRP and your PRF is by adjusting your depth. That's the way that you change these guys. Now you can change this, by the number of periods, blah, blah, blah. But the book specifically says the moment you start messing with your depth, you start messing with these two guys. So that's why, that's why I wanted to bring it up. So PRP inversely related to PRF. Okay. So these relationships are super, super important. Now, when I say this, my depth goes up or my depth goes down, I've learned that students think about something else when I do that. Like they have their own definition of that. So when I say that my depth goes up, I mean you're getting deeper. Some students think because your depth goes up, you're getting closer to the transducer, which means you're getting shallow. Okay. So I just want to clarify that increasing your depth means that you get deeper. And this is why. Increasing my depth means that my depth number gets bigger, which means that at one point, maybe I was at 5 centimeters, and at another point, I am at 10 centimeters. That is a bigger number. And 10 is deeper than 5. And when I say that my depth gets smaller, I mean that my number gets smaller. So if I was at 10 and now I'm at 5, that's my number getting smaller, and that is me becoming shallow. All right, so just wanted to clarify what I mean by increasing depth and my arrow going up and decreasing depth, my arrow going down. I encourage you not to do this in your head. There is no reason why you should be doing this in your head. All you would have to do is write out any formula you know and start going crazy with arrows. That's it. Because once you do that, you can trace things back to where they are. Because if I just say my PRP gets bigger, I can easily just say, oh, look, it's right here. This is going to get like this, and this is going to go like this. There's my relationships right there. All my relationships about depth, PRP, and PRF right there. All right, so don't do this in your head. Just draw out the little arrows. They're going to save you so much time, so much headache, and you can be positive that you're making the right interpretation because you have the formula in front of you. If you remember it, you have it in front of you. And the arrows are simple to make. You can easily like track them and like you can be confident that if one goes up, the other one goes up. That's if that throws you off, then talk to me on the side because it's just little arrows. That's all you got to do, little arrows. Okay. Now, how does this work? How is it that PRP, PRF, and all that stuff starts to mess with things? All right. So what is PRP? PRP is your post repetition period. It's different than your post duration. All right. So here's my post, and I'll draw it out like this. My post duration is this. That is my post duration. It is my on time. It is the time of the post that is on. So if you ever send a voice note, you notice that when you click record and you don't say anything, it looks like this. And the moment you say something, blah, 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 it looks like that. Okay, so that kind of looks like a post, right? And then if you don't say anything again, it looks like this, a flat line. And then you talk again, blah, 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 blah. All right. So for your post duration, it's the little squiggly part where you're talking. And that's why they also call it your talking time. Because it kind of looks like you're talking. So then you have this is your on time. So what is this? Well, it looks like the complete opposite of your on time. Your on time looks like there's something going on, and your off time looks like there's nothing going on. So what is the opposite of on? Off. What is the opposite? Because this is your talking time. What is the opposite of talking? Listening. Right? Talking is the opposite of listening. You cannot talk and listen at the same time. And the post knows that. That's what the post takes breaks, right? It talks, then it listens. Then it talks, then it listens. So you cannot talk and listen at the same time. If in real life you're talking and listening at the same time, you're having an argument. And good luck with that. You know, you know, you're having pretty much an argument. You're going all, housewives on these people, right? That's why. So I watch little funny clips on YouTube. I'm not necessarily proud of that, because, you know, I'm a guy, so I don't really, and I'm not saying I watch those housewife stuff because I really don't, but I like to watch like Gordon Ramsay and stuff like that, and sometimes some reality stuff, and they just start yelling at each other. And as they're yelling, the other person is saying something. So then they start yelling about that new stuff that they just heard the other person say. You know, they're trying to talk and listen at the same time. And that's why it's an argument. So the posters know that. They know better than we do. They know that you can talk, then you listen. Then you talk, then you listen. All right. So that's your post duration right here. So where's your PRP? So your PRP is that on time, which is your post duration, plus that off time. So your PRP is going to stretch from the beginning all the way till it repeats itself. Okay, that is your PRP. It is the time period that it takes your post to repeat itself. Okay, and I cannot stop at my post duration here. I can't stop there because if I stop there, then it means that right after this, my post will repeat itself. So I can't stop there because that's not true. My post repeats itself after the off time. So if I want to know how much time it takes for my post to repeat itself, I have to count that on time plus that off time because then my post repeats itself. Okay. So that is my PRP. It is my post duration plus my off time. It is my on time plus my off time. So how does depth kind of like sneak in, and make its way into here? Because when you change your depth is when you're changing your PRP and your PRF. So this is what's going on. There's something called a 13 microsecond rule, and that's chapter 7 in the book. Come on, spell right, chapter 7. Okay, 13 microsecond rule. And it basically means that it takes a wave 13 microseconds to travel 1 centimeter. It technically travels 2 centimeters, but we're only concerned for that one-way trip. Okay. This is very, very simple. This is just your location. That's it. That is your location. Every 13 microseconds, you are 1 centimeter away. Location. So if something is here, my wave is going to go there, see it, and come back to me in 13 microseconds. Then they'll report to me, hey, there's something 1 centimeter away from us. That is the location, right? You're telling me it's 1 centimeter away from us. What about 2 centimeters? Well, the rule only applies per 1 centimeter. So if I want to know 2 centimeters, then I got to do 1 centimeter plus another centimeter. The time for 1 centimeter plus the time for another centimeter. So for 2 centimeters, it would take 26 microseconds. So my wave to see something that's there will travel there and come back in 26 microseconds. And then it will tell me, hey, I saw something 2 centimeters away from us. So this is all location. Again, time and distance, right? If something is close to you, you can go there and come back quickly. If something is farther away, you need a little bit more time. Farther away, a little bit more time. So let's say that we are 10 centimeters away. That is my maximum imaging depth, 10 centimeters. It will take the wave 130 microseconds to go there and come back. So look how my time gets bigger with distance. And it makes sense. My wave is traveling at a constant speed of 1540 meters per second. It is not getting faster. It is not getting slower. It is a constant. Okay. It's not 100% true, but for the sake of the argument, it's a constant. So if you're going to give me more distance, give me more time. I'm not going to go faster because you give me more distance. All right. Just give me more time. If I ask you to run one lap and it takes you 2 minutes to run one lap, and then I say, hey, give me 2 laps and do it in 2 minutes, you're going to be like, what? You just saw me run one lap in 2 minutes. How do you expect me to run 2 laps in the same amount of time? You know, the fair thing would be give me 4 minutes to run 2 laps. That would be the fair thing. Unless you run faster and you can do it in 2 minutes, but we assume it's a constant, that you're not going to run faster, you're not going to run slower. You're going to keep your same pace. So that's what happens with the wave. The wave has this constant. So if you tell it to go a deeper distance, it says, okay, cool, I'll go there. Just give me more time. That's it. That's it. So back to the whole PRP thing. Let me draw this and this. And then let me draw this. All right, so here's A and here is B. Between A and B, your on time does not change. And that could be a question in the SPI. Your on time does not change. So notice how I made my on times identical. They're both 3 cycles long and they're about the same length. Okay, notice how they're kind of like the same length between A and B. Okay, and then the same thing here. 3 cycles long and they're about the same length. Okay, so your on time does not change, meaning that if I wanted to measure how much time this took, it would be the same down here. Okay, now what you can see that did for sure change was my off time. Okay, look how small it is here and look how big it is here. Okay, so that changed. And because that changed, so did my PRF. So this is how I'm going to bring in PRP and PRF with depth. Okay, because my PRF changed. What is PRF? My number of pulses. On A, I have 3. 1, 2, 3. In B, I have 2. 1, 2. So my number of pulses changed from 3 to 2. My PRP also changed because if I measure my PRP in A, it's from here to here. That is my PRP because right there my pulse will repeat itself. And in B, my PRP is from here all the way over here because at that point is when my pulse repeats itself. Okay, so those things did change. So notice how my PRP in B got bigger, right? Look how long my PRP is. But in B, my PRF got smaller. Okay, and then if you go back to that relationship of depth equals PRP divided by PRF. So my PRP got bigger, my PRF got smaller. So this got bigger, this got smaller. So according to this, my depth should get bigger. It should be a deeper, okay? And that's what I'm going to prove right now. So your off time is your listening time, right? Right here is a short listening time. Right here is a long listening time. And that is what's changing, the off time, not the on time again. So why do I listen for short time here, and over here I listen for a long time? Thing is, what are you listening for? You're listening for reflections. Okay? Everything in ultrasound is a reflection. The whole idea of ultrasound are reflections. If you send something out into the body and it does not come back to you, you don't see it. Your image is composed of reflections. Okay, that's what an echo is. So why is it that you can go to the Grand Canyon and yell out, you know, I love pickles, right? And then hear back, I love pickles, I love pickles. It's because your sound traveled, bounced back to you. Now go ahead and do that on an empty street. Just say, I love pickles. You know, after you get shot and wake up in the hospital, you'll notice that the the reflections never came back to you. You just said, I love pickles, and that was it, because nothing was there to reflect it back to you. Okay, so if you want something to come back to you, it has to reflect back to you. If you want images to be created, they have to come back. If you send something out and it never comes back, you don't see what it is, and now it looks black on your image because it pretends like there's nothing there. But we'll get to that in a little bit later, some other class. So you're listening for reflections. All right, that's what the listening time is. So look at A. A has a short listening time. Short listening time. What does that mean? It means that I expect reflections to come back to me quickly. That's why I'm only listening for a little bit of time, because I expect things to come back. And in B, it has a long listening time, which means that I have to give more time for reflections to come back to me. And that's where depth comes in. If I am shallow, I expect the wave to go and to come back very quickly because I am shallow. This whole concept of shallow and deep only have to do in relationship to the transducer. We call it shallow because we say you are close to the transducer. We call it deep because we say you are far away from the transducer. So if you are very close to the transducer, I expect you to go and come back really quickly because you're right next to me, right? You're very close to me. If your significant other goes to the gas station and the gas station, you know, this is your house drawn to scale and the gas station is right here, right? And let's say that this is a 5-minute drive to go there. So then it means that it's also a 5-minute drive to come back. So your significant other should be back home in like 15 minutes. You know, 5 minutes to get there, 5 minutes to shop, 5 minutes to come back, right? And you know the gas station is close by. So you expect your significant other to go there and come back really quickly. What if it takes an hour? Oh yeah, we slashing tires up in here. You know, like what are you doing that's taking you an hour to go to the gas station that is 5 minutes away? Don't tell me that the line was too long, you know? Like, right? So yeah, something's going down, you know? Now we're gonna be that talking and listening, having an argument. Now that's gonna start happening. So the same thing happens with the wave. Okay. If you are shallow, I expect my wave to go there and my reflections to come back in a short time. And because I expect them to come back in a short time, I should only listen for a short time. So let's say that my imaging depth is 2 centimeters. I expect everything to come back in 26 microseconds. because 2 centimeters is 13 microseconds plus another 13 microseconds based on that 13 microsecond rule. So if I am 2 centimeters away, my machine is going to say, I'm only going to listen for 26 microseconds. That's it, because I expect everything to come back in 26 microseconds if I'm just 2 centimeters away. But let's say that you are 10 centimeters away. Now the machine has to listen for 130 microseconds. That's a much longer time than 26 microseconds. And that is why that listening time gets longer to allot for those reflections that are going to take longer to come back. And it's only fair. Imagine that I'm scanning at 10 centimeters and I'm only going to listen for this much time. Okay, everything that is 26 microseconds will come back to me. And what? I'm going to ignore everything else? What do I do with that information? Where all of those reflections that are coming back, thinking that I'm going to embrace them with open arms. Where are they going? You know? So you have to be fair, and you have to say, if I am going deeper, certain waves are going to come back to me later. So I need to wait and I need to listen for those waves to come back. So that is how your depth starts affecting that off time. It starts making it longer or starts making it shorter, depending on what you're doing. So how does that affect my PRF? Because you see that my PRF change. Well, it affects your PRF because you cannot talk and listen at the same time. So what does that mean? It means that if I am deeper, I chose to listen because I have to. I went deeper, I have to listen a little bit longer. And because I chose to listen, what could have been another cycle right here, I had to get rid of it because I chose to listen. And I can only do one thing. I either listen or I talk. So if I'm going to choose to listen because I'm deeper, then I removed that cycle, that pulse that would otherwise would have been there. So I got rid of that pulse. And the moment you start getting rid of pulses, that's how your PRF starts going down. Because look, I have 2 now instead of having 3. All right, so that is pretty much the relationship between that PRP, PRF, and imaging depth. But all you really have to know is this. This will get you through those questions. And when we get into Doppler and they bring this guy up with this guy, I'll refer back to this formula. But that's really all you need to know. All right, let me check my time. Oh, we went over. All right, cool. So I'll cut it off here. So this is the end of the first session. So any feedback in terms of the pace, the material, the approach about drawing and talking? Is everyone good with that? Because this is pretty much what you can expect for the next 10 sessions that we're going to have. It's really just me drawing, talking, and saying some hilarious jokes. So is everyone okay with that? If you're not, you can always, let me know. But I just kind of want to get if there's any feedback, anything anything someone wants to say, now is your time after our first session.
No, you did good. You gave good analogies.
Analogy guy, that's what they call me.
Yeah, so you did great.
Thank you. Thank you.
I had a couple big light bulb moments.
There you go. That's what it's all about. There you go. Anyone else? Is everyone cool with things so far?
Yeah, this was great. Thank you.
Good. Okay. Awesome. All right. So let me just end this here.